Okay, let me stop here because I want you to well, let's see. All right, let's, but anyway, I just want to point out that we're going to have some new problems that won't be due next week, but I want to give them to you so you can start on them. 5.2, 5.3, 5.8, 5.9. Okay. Now last time I think we had, was it 5.1 due? Which one was the Cottrell equation for the 5.1? So I said 5.1 is not due this week, but we'll have 5.1 due next week. And these other ones would be due in 2 weeks. Okay. So 5.1, yeah, next week. All right, I guess we got some more time here. Okay, let's look again at this problems with the Cottrell equation. That's not a problem, but remember, we want you to illustrate the fact that even though we have a perfectly accurate and valid theory, we have to be very careful about how we apply that theory to understand what it's telling us. And misapplication of theory is really often the major cause of problems with experiments. You can do experiments, it's fine, but if you don't have the right theory to apply to it, or if you use the theory incorrectly, we often have a lot of trouble understanding what's happened. So let's look at our Cottrell equation again. Oh, it's a pi. Okay. Yeah, pi. What else do we have to consider here? Well, another thing to worry about is this term A. It kind of pops in there. We've talked about area before, but we haven't really considered it other than saying, well, the electrode has an area, obviously. Now, the problem of electrode area is not a trivial one, even though it sounds like it. We can think about electrode area in a couple of different ways. One is we can think about the geometric area. And it's often something that people would say, well, I have an area, it's got a radius of 1 centimeter. And so my area is pi, the value is pi. All right, well that's a geometric area. But if actually we looked at that electrode, perhaps it's not so simple, because we could think about that electrode being microscopically rough, depending on how well we've made our electrode and how well we've polished it or something like that. We might expect that at very short time scales, the electrode area could be much larger than the actual geometric area. And in fact, it's not unusual to see electrodes that are 20% larger than the geometric area because of that thing. So we might call AT as the true area. What is the true area? Well, it depends on our measuring stick. You know, it's people that have been interested in fractals may remember this. If you take, let's say I'm going to measure the coastline of England. Well, if I use a 1 foot measuring stick and I go through the coastline of England and measure at 1 foot every way, I'm going to get a bigger area than if I took a 100-yard measuring tape and use that to measure the coastline, because that 100-yard tape would necessarily minimize the actual contour of the coastline. So if we measure the true area, our measuring stick would have to be at least the smallest thing we could think about as using as a measuring stick. And so one way they can do it is to, say, take and absorb some sort of chemical compound on the electrode surface. And depending on how much is absorbed on the electrode surface, that would give us a pretty good idea of the size of the electrode. If we think of a very small molecule absorbed all over that surface, that would give us a pretty good estimate. Knowing how much was absorbed would give us a pretty good estimate of the true area. So this measure of AT over AG is often reported in, especially recently, where people are more and more concerned about the roughness of electrodes. They always have been. A couple of solutions. One is to use mercury. Mercury electrodes are useful for a lot of reasons. One of them, though, is that they are atomically smooth. Although they can have ripples on them, they can have standing vibrations on the surface that effectively cause it to be a little bit larger than you can see. But platinum electrodes or carbon electrodes or gold electrodes all will have some geometrical and true area deviation from unity. Also, our yardstick changes as we change the time scales. So as we make time longer, remember what we said about diffusional distances. Remember we said the mean diffusional path of a molecule is this delta bar, which we can say is square root of 2 dt. As the diffusion time becomes larger, that sort of makes our yardstick smaller or longer. So at short times, what we see for area is going to approach the true area. And you can think about that. If we have an electrode, let's make it very rough. And the molecule is diffusing in, and it's not going to be a linear diffusion, but it'll be linear with respect to the local slope of the molecule of the electrode area. So you can think of that, and then if you just flatten that all out, that would give you the true area. If we make our diffusion much longer time scales, it really doesn't matter anymore. All those little ridges and bumps, they sort of get smoothed out. And so effectively at long time scales, our electrode is maybe just rough in that sort of time scale, and it really hardly makes any difference. So long times, A would approach the geometric area. And so you could actually do this measurement by doing a Cottrell experiment. We could step and look at the current at short times and at long times and compare the difference in the areas and see what the right area is, or whichever one you prefer to use. The problem is at short times we often have to worry about this charging current and the potentiostatic limitations, and at long times we have to worry about these other things. So you have to be very careful in these sorts of experiments to correctly account for the other problems that you're going to have. Actually, a better way to do that is to measure what they call an adsorption. We already said that just by looking at the Cottrell, the chronocoulometry experiment, we can get adsorbed amounts. And so Q, the measured amount of charge, is going to be equal to 2 times NFA geometric dO C0 star T to the 1/2 plus terms that are due to the double layer charging, plus what we're really interested in is the charge due to the adsorbed molecule. And remember, that's NFA true gamma adsorbed. And it's true because our molecule that's being absorbed is very small, so it effectively will cover completely no matter how rough our electrode is. One nice one is a molecule called methylene blue. Sticks to lots of electrodes, carbon particularly, it sticks very nicely to, and platinum. And that just sort of lies flat right on the surface, and by knowing the true shape of the, shape of the absorbed methylene blue, you can get an idea of the molecular area, really the coverage of the methylene blue, and then knowing how much current flows when methylene blue is oxidized or reduced, then we can get a charge and then the amount of coverage. That's a 2-electron process, by the way. Another common experiment to get areas is to use sometimes more easier to do, and although not always. Platinum electrodes work especially well for this experiment. Remember, platinum in a strong acid solution, there's large amounts of protons in this acid solution, and remember the proton reduction is a very rapid process on platinum. So if we do a current potential curve, we see a current that really takes off. That's the reduction of protons to hydrogen gas. And then at the other side, we see oxidation of water to form oxygen gas plus protons plus electrons. Now, in this region here is often called the double layer region because they're saying there's very little things going on. But in fact, if you blow that region up so that that current is larger on that scale, what you see is curves that look quite a bit different than what we've drawn. In fact, I'm going to see if I can draw more accurately. Of course, you're looking at it on the thing, but what you see right around 0 volts is curves that look something like this. Now this would be a milliamp per square centimeter current density. This would be microamps per square centimeter. So we're talking about 100 or 1,000-fold change in the scale here. Now this, of course, is the reduction of proton. And this would be, if we continued, would be the oxidation of water. But what about these other things that are shown up here? Well, turns out that this is an absorbed hydrogen atoms or ions on the surface of platinum. The hydrogen ions actually absorb quite strongly on the platinum. There's a monolayer coverage of these hydrogen atoms on the ions on the surface of the platinum. And so what you find is that you take the hydrogen ions and in the presence of platinum and 1 electron, you form a monolayer of adsorbed hydrogen atoms. And so that's what you're seeing here is the reduction to form adsorbed hydrogen atoms. Now, as soon as the monolayer of adsorbed hydrogen atom is formed, the current can no longer flow because we're not allowing that reaction to occur anymore. So we get 0 current then. But by looking at the charge under these peaks, for example, you can get the amount of hydrogen that's absorbed under the surface and understanding a true idea of the geometric area. So the charge associated with hydrogen is about 210 microcoulombs per square centimeter, or approximately 1.3 times 10 to the 15th atoms per square centimeter. And that's on a particular type of platinum surface of single crystal platinum 100 crystalline face of the platinum. It depends, these wave shapes actually depend on the type of platinum crystalline surface that's exposed to the solution and some other things. And they're very dependent on the purity of the solvent. If you have even tiny, tiny amounts of impurities, organic impurities, these peaks shift around and are not in the same place or not as large, or they're shifted. And that is a good diagnostic test for purity of the solution. So people often use the shapes of these peaks and the sharpness of the peaks as indications of solution purity or electrode polishing, good electrode polish. This part of the peak over here is oxygen, platinum being oxidized to platinum oxide, and then that oxide being reduced off of the surface. And again, we just get a monolayer of this platinum oxide, and then it reduces away back to the platinum metal. And so you could also use this peak or this peak to get the electrode area as well. But usually they use the hydrogen peaks. So that's very diagnostic for platinum. Now for other materials like mercury, we don't see those peaks because we don't see absorbed hydrogen atoms in mercury. Gold and palladium, we'll see peaks similar to these, although different than in shape than these. All right. Well, I thought we could do a little bit of a program that I wrote, show you a little bit more clearly the Cottrell behavior. Are we got a tape? Why don't we stop here then and why don't we take a little bit of a break and